So at this point, we have covered quite a large part of the features offered by the DSAnalysis Matlab Toolbox. There is a few things that we haven't done yet, is working with a delayed system and working with a three-phase system. So I suggest we do that. Let's go back to the main. And let's check what I have implemented for the single phase MMC, but with this time control delays. And we'll compare it with what we had for the non-delayed systems, at least in the structure of the files. We can create a new DSA. Naturally, if I have previously worked on this system and if I have saved the DSA structure, I can reload it and restart from where I had left. In this case, I have no saved DSA structure for this particular instance, and so I am creating a new one. It has the same number of states, inputs, and output variables as before, I think, but in any case, the major difference is that this time it has two delay variables. Okay, as before, instead of looking in all the folders for the user-defined files, I can simply go to DSA, function handles, and open. Instead of opening all of them, I would like to simply open the equations file. There it is. So the structure is the same as for the non-delayed system, except that this time I have an additional structure from which I can get the delayed variables. I have defined as being delayed the upper arm insertion index and the lower arm insertion index. And then instead of having, as before, just the actual insertion indices being equal to their reference values, this is only the case if the system is not delayed. So if the system is not delayed, then the insertion indices are equal to the reference insertion indices. If this is not the case, well, simply we will not enter this if statement. We see that we do define the reference insertion indices, the one that will be delayed or can be delayed, but I am using the results but I'm using the delayed versions of those insertion indices, which are provided by the delayed structure. So let me say that again. We calculate non-delayed versions of the modulation indices or insertion indices, but the actual version, the actual values of these indices are only equal to these reference values if the system is not delayed. If it is delayed, they come from the delayed structure. Okay, so to make all of this work, I have to also modify the lists of variables. So before, these two cells were empty. Now they are filled in with each two variables. I have defined the two delay variables, which are the variables that are subject or subjected to a delay. They will be delayed. And I have the delayed variables. Those are the versions that are delayed. So this is how the vars or variable file is modified. And actually I have to specify it for each of these variables. What is the delay? Is this 50 microseconds? Is this 150 microseconds? This is something that I can define in the data file. There it is. So it is exactly the same as before. Actually, I have already presented the way I worked in this particular file. I have defined a time delay in microseconds just to make things easier. I know that US is microseconds, so 150, and then I convert it into seconds by multiplying with 1 to the minus 6. I have here delays defined for another instance, a three-phase model, but actually, since I have defined in the list of variables only these two, then the toolbox knows that it has to look for these variables in the delay structure. Okay, and then how does this work? Well, I just said that in this delay structure, which will be set in the data, I assign this particular delay value to this particular variable. Let me also specify one thing. The order is important. The order is important because the first two delay variable will give the value of the delayed variable of the first delayed variable, and the second is also related to the second, and so on. Let me also specify something that I have not said earlier, but the order is also important for the states. It is important because in the list of equations, or in the differential equations, the first equation is related to the first state, the second equation is related to the second state. So when linearizing, so when calculating Jacobians, it is very important that each differential equation be related to the states in the order in which they are specified in this particular cell. So it is important to keep track when you change this list that you have to update this vector of analytical expressions, and if these equations are sorted in another way, then also you will have to update the order of the states in this particular cell. Okay, so at this point we have defined a delayed system, and there are many things we can do with the delayed systems, basically everything that we have done so far with non-delayed systems. I can solve again for harmonics for the periodic trajectory of the MMC with up to harmonic rank 6. I will also work with analytical model. If you recall, I have to set it to 1, otherwise it will not work. I run it. I check that the error of the collocation method is very small. This is the case, so it is good. Naturally, this time I do not have the eigenvalues of the Jacobian because in this particular case, the eigenvalues of the Jacobian are not characteristic roots of the system because it is a delayed system. So this is one important difference. If we want to have eigenvalues, or more precisely characteristic roots of the delayed system, then we will have to use the DHSs, so delayed harmonic state space representation, and a dedicated algorithm based on the delay Arnoldi algorithm, which is also known under the name of iterative infinite Arnoldi algorithm. We will have a look at that later. In any case, the collocation method has converged. The equation is solved. And again, for a very small system, it is very fast. And as usual, we can find all the results in the as time domain waveforms, as harmonic domain data, as well as with the plot. I'm looking for a collocation waveforms, so I'm uncommenting this one. I would like to have no density reduction, all the points, and I can check the results. So I have again the same 4 states as before that I have defined as a set of variables, but this time I would be interested in knowing if the code has actually accounted for the delays. So I can look at the insertion indices, but also what I can do is check if I have more variables available. Of course, while I have, also the references which are not equal to these values. So I can include them. It's either like this. I say that this is now a set of variables and I can observe their waveforms. I see that blue and red are the references, yellow and purple are the actual values, and indeed in between I see that there is a delay which is equal to 150 microseconds. This is something we can check, for instance, between this point and this point.